Hi everyone. So welcome back to another Math 230 232 GSG session. Today we'll be covering chapters 16.4 and 16.5 today. All right. And I apologize for the inconvenience earlier. There was something that came up and I couldn't have the session at 5:45. But okay, let's get straight to it then. So let's start off with 16.4. Okay. So 16.4 was basically the introduction of Green's theorem. And we'll start off with evaluating line integrals by using Green's theorem. So yeah, start off with 16.4, number 3. And again, I'll be referring back to these questions from the textbook. Okay. So let's get started. So 16.4, number 3. All right, let's see what we have. So for number 3, we're given this closed integral with bound c, where the function inside is xy dx plus x squared y cubed dy. All right. So, and we are given that c is the triangle with vertices 0, 0. So I'm just going to draw this diagram. So for the bounds, they give us that it is the triangle of vertices 0, 0, 0, 0, 1, 0, and finally, 1, 2. So this is what C represents for this question. All right, so it tells us to evaluate by using two methods, one directly and the second way using Green's theorem. Okay, so I'm going to start off solving this directly. So by solving this directly, I'm going to clump up these sections or label these sections as three different parts. This as C1, this as C2, and finally this as C3. Okay. In counterclockwise direction. All right, so for part A, now C1 is, I'm just going to write its parametric equations. I'll represent x, I'll set x equal to t, right? While dx is equal to dt. And as you can see over here, since I'm labeling x equals to t, I can say that the domain for t is going to be bounded between 0 and 1. Okay. While as you can see for C1, that y stays at a constant level of 0, and hence d of y is also going to be 0. Okay, so that's C1. Now for C2, segment C2, we have that x stays as 1, right? So we can represent x is equal to 1, while dx is equal to 0. But y does change. Yeah, I can set this y equal to t, but then my domain for segment C2 is going to be between 0 and 2. Okay. And then again, dy would equal to dt. And then finally, for segment C3, we have that x is equal to 1 minus t, right? Since we're going from this vertex down to 0, 0, I can set x is equal to 1 minus t and set the domain t to be bounded between 0 and 1, while having y starting at a position of 2 minus a slope of 2 times t. All right, so we have those three segments set up, and so we can say that we have integral of C1, right? Integral of C1 of the function. Let me just represent this as f of x. And then, so we have C1 f of x, or fx comma y, sorry. more accurate, I'm just gonna label this fx comma y. Right, so let me just write it all down. So let's see. So for the first part, I can say that, right, for C1, we have the lower bound of 0 to an upper bound of y. And if we plug these parametric equations back into our function of fx comma y, we notice that the first chunk is actually going to be 0 plus 0. Yeah, so we just have 0 for C1, the integral of 0 for Z1, C1 for the first segment. Then we're going to add this to the integral of the second segment. So I'm just going to set my lower and upper bounds as 0 and 2. Now, if I set my function fx comma y using the parametric equations I have 1 times t times 0. So we have now 0 plus x squared, which is 1 t cubed times dt. All right, and then, yeah, so we'll be left with t cubed there, and then the last segment from 0 to 1. So we have x as 1 minus t, y as 2 minus 2t. Now dx is gonna be -1, so negative dt, plus x squared, so 1 minus t squared, and then 2 minus 2t cubed, cubed, and then dy is gonna be -2 det. Okay, so let's see if we can solve this out. So yeah, for the first part, it'll just be 0, right? So we're just gonna be constant, so now that's gonna be added to the integral of 0 to 2 for the first part's gonna be 0. This just cancels out. It's gonna be left with t cubed times dt, and that's gonna be added to the integral from 0 to 1 of, let's see, so yeah, 1 minus t. Let me split this up into two different integrals. So I can use this as 1 minus t times 2 minus 2t dt plus the integral from 0 to 1 of 1 minus t squared and 2 minus 2. And let me just shift this over. Plus the integral from 0 to 1 of 1 minus t squared times 2 minus 2t cubed times -2 dt. Okay. So yeah, this would be basically how we set up this question. Okay, and then we can expand this out. We can just take this integral, expand this out, take the integral. Now for this one, let's see. So 0. Yeah, I guess we could set it up. Just give me a minute. Yeah. All right. So yeah, let's actually solve this out. So you know what? I can do this actually. One. All right. Yeah. Okay. Yeah, I think that's it. Yes, I'll just leave it as that for now. Okay. Okay, so yeah, this would be my answer for part A. All right, now let's look at solving the same question but using Green's theorem. So with Green's theorem, I'm just gonna write this down again. We have that when we have a function bounded by c of p times d of x plus q times d of y, that's actually going to be equal to the double integral bounded by d of the partial derivative of d of q in respect to x minus the partial derivative of p in respect to y of d of a. Okay. So for this question, again, I'm just going to write down the question again. We have the closed integral of x y dx plus x squared y cubed dy. Then we have the double integral bounded by d. Now, based off this formula of Green's theorem, we can say that we have the partial derivative in respect to x of x squared y cubed minus the partial derivative in respect to y of xy, right? And all in terms of d of a. Now that is going to equal the double integral of, is that 2x y cubed? Yep. Minus x, and let's say d of a is dy dx. Now if you look back at the bounds, you can notice that y actually starts off at 0, right? Based off that triangle we have over here. Y starts at 0 and goes up to 2. And let's say that x is bounded from 0 to 1. So what we can say is y is going to be bounded from 0 to y is equal to 2x. So I'm just going to label it like that. X is going to be 0 and x is going to be equal to 1. All right, so now if you actually solve this double integral, we get that, so we're going to close 0, 1. Now 2xy to the power of 4, right? Yep, 2xy to the power of 4 over 4 minus xy from 0 to 2x d of x. Now that's going to simplify down to 0, 1. Now that's just going to be 0 for the bottom part. And for 2x, we get that 2x is multiplied by 2x power of 4 over 4 minus x times 2x. Okay. Of dx. Now that's going to equal the integral from 0 to 1 of 2 power of 4 is going to give me 16, so 32 x power of 5 over 4 minus 2x squared of d of x. Okay. And then if we solve that out, that's going to be, so that's going to be 8x power 6 over 6 minus 2/3 of x cubed from 0 to 1. So that is going to yield an answer of 8 over 6 minus 2/3, which is the same thing as 4. So 8 over 6 minus 4 over 6, which is going to give me 4 over 6, which is the same thing as 2 over 3. Okay. So yeah, so for this question, solving the two methods will yield a solution, or should yield a solution of 2/3, either directly or using Green's theorem. All right, so let's try another one of these kind of questions. All right, I'll be looking into number 5 from the textbook. All right, okay. So for number 5, they give us that, so it says use Green's theorem to evaluate the line integral along the given positively oriented curve. So we're given this integral bounded by c of y e to the power of x dx plus x squared, or no, plus 2ex, sorry, 2e to the power x of dy. Now c is going to be the rectangle with vertices of 0, 0, 3, 0, 3, 4, and finally 0, 4. 4, 3, 4, and 3, 0. Okay. All right, so we have that so far. So it's actually going to be this rectangle right here. Okay, so we'll start off with that. Now, yeah, so it says to use Green's theorem. All right, so again, by using Green's theorem, I can rewrite this question as the double integral bounded by d of the partial derivative in respect to x of 2e to the power x minus the partial derivative in respect to y for y e to the power x. Right, and then yes, this would be d of a. All right, so let's see. So we got the double integral. So that's going to give us 2e to the power x, and this is going to give us e to the power x of dy dx. Okay. Now for y, we notice that it goes from a bottom or a min of 0. The rectangle given is starts off at 0 and it goes to as high of a y value of 4. If we label this y and label this x, and for the x, we're bounded between 0 and 3. Yes, 0 and 3. Okay. All right, so we have to set up. And so what you want to do next is just evaluate the integral. Let's see what we get. Okay, so we have 0 to 3 for x. Now we're going to get 2y e to the x minus e to the xy, or y e to the x, going from 0 to 4. And then multiply by the x. That's going to give us the integral from 0 to 3 of 8 minus 4. So we have 4, yeah, because we have 4 e to the x of dx, which is going to give us the same thing, 4 e to the x minus from 0 to 3. Okay, so we have basically 4 e to the 3 minus 4. And I can simplify off to 4e cubed minus 1. All right, so that was number 5. All right, so let's continue with number 11 from the textbook. All right, so, okay. So for number 11, we're actually going to incorporate some of the ideas we learned from the previous sections. So yeah, it says to use Green's theorem to evaluate the integral bounded by c of f dot dr. So again, if you remember, this actually represents work, right? So because we were given a unit, a force vector, sorry, we're taking that and the distance vector, and we're doing a dot product across them while integrating. So that's gonna yield the work done. So yep. So for number 11, we get that the force vector of x comma y is going to be the same thing as y cosine of x minus xy sine of x. Well, the y component is going to be xy plus x cosine of x. All right. Now c is going to be the triangle, so they also give us they give us the bound c, where C is going to be the triangle from C is going to be triangle from 0, 0 to 0, 4. Oh, sorry, 0, 0 to 0, 4 to 2, 0. So I'm just going to write that 2, 0, and I'm back to 2, 0. So going in the clockwise direction for this. And it is actually important that we remember that for this question. Okay. So yeah, I'm gonna start f at 0, 0. We're gonna go up till 0, 4, go down to 2, 0, and finally back to 0, 0. All right. And that tells us basically to find the integral of f dot dr. Okay. Since we're going in the clockwise direction, we have to make sure that we go back in the counterclockwise direction for a positive result. So we want to set the negative of negative c, and taking into account the the force vector we're given, that's going to be y cosine x minus xy sine x. Now that's going to be multiplied to d of x plus xy plus x cosine x of dy, right? You want to make sure that this, I'm just going to highlight this part right here. Yep. As you go through, or like when you draw your vertices or your bounds that you're given in the question, you want to make sure that it's going in the counterclockwise direction. And hence that was what essentially what I was doing, where I set the integral as a negative. So you're flipping over the direction of the orientation of the curve before I apply the theorem. Okay. Okay. So then we go on and we solve it just like just like we have previously done using Green's theorem. So again, this is equal to the negative this double integral. I'm going to say bounded by d of the partial derivative of x of xy plus x cosine x. Now that's going to be subtracted by the partial derivative of y of y cosine x minus xy sine of x. Okay. All right, and this is all going to be in respect to d of a. All right, so let's see what we have. So that's going to be the negative double integral of y plus cosine x plus x or times negative sine of x. Negative sine x. Yep. Yeah, negative sine x. Why is this not working? Okay, there you go. So that's going to be subtracted by the partial derivative of that in respect to y, so cosine x plus x sine x. All right, the a. Then finally, we're going to yield the double integral of, so the x sine x actually cancels out with this x sine x. And then we see that this cosine x actually cancels out with that cosine x. We're just left with y times dy or dx. All right, so now let's actually look at the bounds for y. So y actually is bounded between 0, right? We're going from 0, and it goes to a maximum value of 4. So it goes, so I can rewrite this, or I can rewrite this curve as y equal to 4 minus 2x, right? So that's going to be my bound for this region right here. And for x, we're going from 0 till 2. Okay. So let's see if we can solve this integral. It's going to be run from 0 to 2 of 1/2 y squared 0 to 2x, or 4 minus 2x, sorry. Dx. And that's going to equal the negative integral of 0 to 2. What is that going to be? 1/2. So 0 to 1/2 of 4 minus 2x squared dx. Okay. That's going to give us -1/2 the integral of 0 to 2 of 16 minus, so what's that going to be? That's -x, 8x, or yeah, -8x. No, sorry, -16x. It's my bad. -16x plus 4x squared. Okay. All right. And then, yeah, you can just continue and solve that integral right there. Okay. So this is essentially, yeah, connecting what we learned before regarding this theorem right here and applying Green's theorem doing this question. All right, so that's number 11. All right, let's continue with number 13 from this chapter right here. Yeah, okay. So yeah, same section, same part of the 16.4. We're just going to use Green's theorem to evaluate the integral of f dot dr. Okay. So for number 13, we have that the vector f comma y is equal to y minus cosine y comma x sine y, and then we have that that c is the circle x minus 3 squared plus y plus 4 squared, which is equal to 4. Now it's important that they mention it's oriented clockwise. Okay, again, refer back to this right here when we set up the integral. So what we can see from the given region of C, we have a circle at center 3, -4 with a radius of 2, right? Yeah, this is just based off the general formula of a circle. Okay. All right, so again, what you want to do, just like the previous question we just set up the integral, right, in terms of dx and dy. And since, again, our orientation of the curve given is clockwise, we have to make sure that this is actually going to equal the negative of the integral divided by -c of, so we have y minus cosine of y dx plus x sine of y dy. Okay. And then now applying Green's theorem, we have the double integral of d. Now we have a partial derivative with respect to x of x sine y. Right, x sine y. Now minus the partial derivative of y minus cosine y. Okay. And all of this is in respect to d of a. Now, if we simplify this down, or if we compute the partial derivatives, we get that we have sine y minus 1 minus the cosine of, sorry, I forgot the negative in front. Right, negative carries on from this, right? Sine y minus 1 plus, or minus actually, minus sine y. Right? Yeah, minus sine y. And what we notice from this is that we have the sine y's canceling out. So we're actually just left with the double integral bounded by d of d a. Now, this is actually just gonna, yeah, this should just relate to the fact that this is the area of d, or the boundary region that we're given. Now, in the question, we're given this area of we're given this bound C, which is a circle, right? So we're just essentially finding this area of a circle. So now just using the formula of area of a circle, we have that the area is equal to pi times the radius, which we said was 2 squared. And hence the answer for this question would just be 4 pi. Okay. All right. And yeah, I think that wraps it up for 16.4. Okay. So now let's move into a bit of 16.5 today. Okay. All right. So 16.5 was the introduction to curl and divergence. So we'll cover, we'll start off with number 3 from 16.5. 16.5, number 3. So it tells us, or it gives us, that the force vector of x comma y comma z is equal to x y e to the power of z I hat plus y z e to the x k hat. Right. Now it's asking us for part A, it tells us to find the curl of the given, the curl of f. Okay. All right. Just from the definition of the curl of f, this actually means the del operator, as covered in lecture, cross multiplied by the force vector. So if we set that up, we can let's set up the ijk. Now the first vector is just going to be the operator, so it's just going to be the partial derivative of x, partial derivative of y, and finally partial derivative of z. So we have that for the first vector. And for the second vector, we have xy e to the power of z, 0, and yz to the power e to the power of x. So if you compute that out, the the resulting vector is actually just going to be, so if we cross I out, left with the partial derivative of y z e x, so that's just going to be z e x minus 0 I hat minus, remember the middle term is going to be a negative, now that's just going to be y z e to the x minus x y e to the z j hat. Okay. Finally, that's going to be added on to 0 minus x e to the z k hat. So we can simplify this down. That's going to be z e to the x I hat minus y z e to the x minus x y e to the z j hat added or subtracted by x e to the z k hat. Okay. Yeah, so the biggest thing for curl is just remember that it's the cross product between the del operator and the force vector. Okay. All right, so now let's look at part B. So for part B, we're supposed to find the divergence of the vector field. So div of f. And again, this is equal to the del operator. Instead of cross multiplying, we're just doing the, instead of cross product, we're just taking the dot product with f. Okay. All right, and so that is actually equal. So let me just set it up real quick. So we have the partial derivatives as a vector dotted with x, y, e, z, comma 0, comma y, z, e, x. Right, remember, the dot product will yield a scalar multiple instead of a vector. Or not scalar multiple, sorry, scalar product instead of a vector product. All right, a vector result, yep. All right, so, so we're basically gonna take the partial derivative. So that's gonna be y, e, z plus 0 plus y e to the power of x. So if we can factor out a y, and we're left with e to the power z plus e to the power of x. Okay, so that's gonna be the divergence of the vector field. Okay, so the two biggest things, at least the intro to this chapter is going to be these two definitions as covered in lecture. Okay. All right, let's do one more before we wrap up today's session. All right, so let's do number 4 for 11.5. All right, let's look at number 4. So number 4, essentially doing the same thing. Now the force, the vector field they're giving us is sine y z I hat plus sine z of x j hat plus sine x y k hat. Okay, so for the curl of f, that's just gonna be the cross product. So ijk. So partial derivative of x, partial derivative of y, partial derivative of z, with sine yz, sine zx, finally sine xy. That's just going to result into cosine of xy times x minus, right, sine, so cosine of zx times x. All right, that's going to be I hat minus, so that's going to be subtracted with 0, right, because there's no z term here. That's just going to be 0 and minus sine y of z times y j hat, and finally added on to, so cosine of zx times x minus cosine of yz times z. Yes, k hat. Okay. So this is going to be the curl of the vector field. Okay. And clearly, yeah, you can try and simple it out, but yeah, I'm just going to leave it as that. And then finally, we're going to find the divergence of the vector field. So again, we have the del operator as a vector, and then we're going to take dot product with sine y of z, sine z of x, and sine xy. Okay, and that's going to yield the answer. So for the first term, I'm actually going to get 0 plus 0 plus 0. Right, yeah, so yeah, that's actually just going to give us a divergence of 0 for this question with this vector field. Well, all right, I guess that wraps it up for today's GSG session. Thanks for tuning in. If you have any questions, just feel free to message or to post a Piazza post. All right, thanks for tuning in, and I'll see you next week.